I'm Professor Byron Gates in the Department of Chemistry at Simon Fraser University. The advent of electric vehicles has spurred the need for batteries with high energy densities and increased power. Lithium-ion batteries are one of the most sought-after energy storage solutions of our current and future needs. Many challenges, though, have hindered advances in battery technology. Safety is one of those concerns that you might be aware of. Another is a relatively short lifetime. We're working on materials to improve the durability, power density, and overall performance of batteries. And we do this through customized coatings, tuning the fine atomic scale features and composition of these materials. Today, we will cover some of the most important aspects of preparing and characterizing lithium-ion batteries.
Electron microscopy facilities enable us to discern the atomic composition and structure of our materials. We use a scanning electron microscope or SEM to create high-resolution images, such as to view the shape and size of our crystalline materials.
A complementary technique is transmission electron microscopy, or TEM, that projects a beam of electrons through nanoscale samples to observe atomic compositions and crystal structures of our materials. We can use TEM for careful analysis of the surface of our cathode particles, particularly used to characterize surface modifications like coatings that can enhance capacity and durability of the batteries.
Here, Cathay is preparing the cathodes for our coin cell from inks containing nanoparticles with custom coatings such as phosphate-based materials. Our cathode materials include lithium iron phosphate, nickel manganese cobalt, and high voltage spinel composed of nickel and manganese with a tuned atomic ratio and structure. Slurries of these materials are cast as thin films which contain carbon nanoparticles for improved electrical conductivity, binders to stabilize the inks, and additives that enhance ion stability and migration. These micrometer thin films are cast on planar aluminum using a high-speed coater with a robotic arm. After removing residual solvents, these thin electrodes are cut into circular sections with a precise diameter and thickness, which are transferred to a glove box containing an inert atmosphere for further handling and assembly into coin cells.
This rather funny-looking instrument here is our glove box. It allows us to handle our materials and assemble coin cell batteries under an inert atmosphere of argon gas. This chamber is essential because the anode material we use, lithium metal, is very, very reactive with air and moisture. Lithium metal is used in research lab environments because it is a well-understood reference or control to compare our cathodes against for study. Lithium metal is not used in commercial batteries, though, because of the high fire risk. In the main chamber of the glove box, we assemble the coin cells. There are 8 parts to these coin cells that I will demonstrate here on the benchtop. These parts include stainless steel casings, a top and bottom cap and can of the coin cell, a spring and spacer to adjust the physical contact of the parts within the assembled coin cell, the lithium metal anode, a polymer separator which prevents short-circuiting of the battery, electrolyte that assists with lithium-ion transport from positive to negative electrode, and the cathode materials that we've prepared and coated onto aluminum support. The anode and cathode and separator have each already been cut to fit easily inside the coin cell casings for simple assembly. A hydraulic press is used to form an airtight seal and crimp all components into the final coin cell. This results in a nice compact cell which looks much like a watch battery and is safe to handle in air.
Here, I demonstrate the testing of fully assembled coin cells using a battery cycler. There are several requirements sought in advanced lithium-ion batteries. These include a high capacity and high reaction kinetics of our cathode materials, and reactions occurring at the cathode materials that do not affect or contaminate the system. The lithium electrode itself should not adversely affect the overall potential of the cell and the reliability and stability of the potential over time. A key performance metric for the battery materials is their C rate, which describes how fast a battery is charged and discharged, and that is for rechargeable cells. The capacity of a battery decreases with faster charging rates. A series of charging rates are evaluated for each coin cell and help to compare the effects of different coatings our teams are preparing to improve the performance of these materials. For this evaluation of stability, batteries are charged and discharged hundreds of times, and changes to the capacity is measured as a result of these experiments. Generally, batteries should be replaced when their capacity loss is greater than 20%. It is important to keep batteries out of landfills. British Columbia has been home for many years to some of the leading battery recycling companies in North America. We need to ensure that our materials continue to get to these companies, but we also need to keep in mind the recycling needs as we prepare new battery materials.
Evolving away from our reliance on fossil fuel-based economy will require action across all sectors of society. Batteries are assisting to enable electric vehicles and to support our transition to renewable energy sources. Energy storage, whether for portable or stationary needs, will require battery materials that last longer and offer higher energy densities and power than those currently available. These advances will require a multidisciplinary approach.